Okay,
We are live.
so I'm late.
No, we are live.
Live.
Okay. So today's session we're gonna finish off with groups, and I'm gonna. It's going to be hopefully a quicker session. It's going to be a little bit, I think, less interesting, except for the end, because we'll start it off with. We'll actually go back to define functions properly, and then we'll end up with like the first isomorphism theorem for groups. Okay, which is, I think, the interesting part. Yeah. Okay. Let's get going. All right. So we define a function as a mapping. Okay, mapping between really two sets. Okay. We denote it like this. So this would be the mapping f between from set x to set y, and then the function itself, we usually we write this, which you should not really know. Actually, I'll do it like this. Right, so it's like x is from x and y is from y. There are also other formats like that you may see with this, like this arrow with like an n. That's also a format that you'll see sometimes for defining the actual function. Okay, we call x is typically called the domain of the function, and y is actually, by correct terminology, it's called a codomain. Okay. A lot of times we call it the range. The range has got a little bit, even though the range is y, it's got a little bit of it's a slightly different terminology or definition, and we'll see it a bit later on. Okay. Do we need examples?
No.
All right. Now let's go. We'll go through like a lot of definitions of functions, and we'll try and do it quickly. If there's anything that is not understood that you want to go deeper into, anyone, and just stop me. Okay. So function has to actually satisfy three things. Okay, you don't need to remember them. You probably like intuitively already know them all. One is called totality. Okay, totality is that actually for every x in x, right? There exists y such that f of x equals y. Okay. So there needs to be a y for every x that obeys. That's totality. Existence. It's actually just, I guess, the other side, that for every x, right, f of x is in y. All right. Right. Okay. One talks about the existence of x and one about the existence of y, and there's actually an example here that clarifies what the exact differences. And then the last one, which is perhaps the most important, is actually uniqueness. And it means that that actually for every x there's only one y. Okay.
Right.
So we can have like the same y for two x's, but we can't have it for like two y's for one x. Okay. So if f of, maybe I'll write it like this, if f of x1 equals f of x2, then necessarily x1 equals x2. Equals x2. Okay.
לא,
No,
פתאום.
the other way.
הפוך.
Alright.
לא, אם f של x, if fx,
Sorry.
if fx
Yes,
equal
yes,
y1
yes,
and
yes,
fx
yes.
equal
You're right.
y2, then
Sorry.
y1
You
equals
just needed to put the arrow the other direction.
Yeah. You're right. If x1 equals x2, then necessarily, right, f of x1 equals f of x2.
Yeah.
Okay. Bit of a funny way to maybe present it, but you understand. Let's just look at one example for totality and one example for existence, because this is clear, I think. So if I define G from R to R, okay, and I define it with G of X equals 1 divided by, say, X minus 1, okay, then I've got a problem with totality because I cannot define G of 1, right? G of 1 is not defined in R, and that, okay. So maybe this can be corrected if maybe I expand R here, right? But, yeah. So that's a problem of totality, okay? It means that I don't have the G of X, I do have X, but the G of X creates something that, now, existence is very similar, okay? Let's define f from n to n, okay? And we'll define f of x, or maybe of n, I mean, it doesn't really matter, but, yeah. Equaling n minus 1. N minus 1, okay? Right? So n is a natural number, it can't be 0, okay? And again, the assignment fails, yeah. Okay, let's continue. But I think most of the time, the thing that interests us most is uniqueness, okay? All right, identity function is just a mapping of f of x to x, right? Such that f of x equals x, right? This is called identity. And there's also something called like the empty function, which is whatever, like the empty set maps to any set that you want, right? That's an empty function. And that's just to be complete. Okay. All right. The image we can talk about, and this is actually important. So we can talk, if we've got f of x to y, okay, we can talk about the image of u in F, okay? And I guess, I mean, we can, we'll see that there are a few terminologies, but the image of U and in F is actually F of U, okay? The image always is like a subset of Y, okay? Right. And obviously, right, we're assuming that U is in X, right? But when we talk about the image, we're always talking about a subset of Y. And we usually call F of X, okay? So this is taking like it's the largest image. We call that the range of the function. Now, why is that different than the codomain? Because actually the codomain can be bigger than the range, okay? So it's all these subtleties. So we can say that the range of F, okay, which is this, right, is actually in Y, in the codomain. Right? Now, we'll see that a lot of times, this full image, okay, is also referred to, you'll see things like this, image of F, okay? And when you see this image of F, it would mean the full image, or the range, okay? All right.
So
It does get a little bit more interesting.
range and image is the same.
You can say that the image of F is a set, yeah? And if range of F is also a set, then yeah, you can say that they're
The
equivalent.
same.
Yeah. Okay. All right. Okay, there's something called a restriction. It's not so important for us, but a restriction would be if I take F from X to Y, right, and I want to define a restriction on U, then I would usually mark it as, I think it's something like this, or like on group U, it would actually define, like, I'm not gonna write anymore, but it'll actually define like the sort of like sub-function, right? It would define a function from U to Y, okay? That is the subset of this function, okay? So it's no longer a set. The restriction is actually another function, and it is useful sometimes, but not so much in our future context at the moment. Maybe. We talked about image, we can talk about pre-image, and this is important, okay? So imagine that we have,
Yuval,
yeah,
when you define the, what do you call it, the subset function? Sub-function?
Restriction.
Yeah,
restriction.
restrictions. So you have to make sure that still for every Y there exists an X, right? Because
You assume that U is a subset of X.
Yes,
So
but
if-
with the three
yeah,
characteristics that you said, you need to tie it
Y
in.
is the same Y. You don't change Y.
But you make X smaller. So maybe
Yeah,
now,
you essentially take. Just imagine if you think of a function as a mapping, it means that you're basically getting, you're shrinking X, and you're also getting rid of all the mappings that came from like X's that are not U.
so you're shrinking Y too.
Potentially you'll just get points in Y that are not connected to anything. They're not in the range.
Ah, but you said existence means that for every y there's an x.
No, existence means
No.
that the image is in the Y.
Yeah.
Yeah.
The image is in
You're allowed to have, okay, let's
F of x is in y.
let's just take an example, okay? You can have, for example, the function, like this is legal, z to z, all right, with like f of x. We always assume that x is the domain, y is the codomain by default. F of x is, for example, I don't know, 2x or x squared or something that doesn't cover the whole codomain. But we still, this is the codomain, it's not completely covered.
So where's the totality and existence here?
I think like there was a line he wrote and then he erased it, right? You like, I think.
Okay, so, you know what, I think that there is a very subtle difference between totality and existence, but I need to think about it. It's that they're both defined over existence in Y. Okay?
For every x there's a y, but it's not true that for every y there's an x.
It's not true that for every Y there's
No,
an
that's
X.
the
So only
example n minus 1 of the natural one, as there is no existence from 1.
Right. It's
And here there's no
Totally.
existence for...
it's
Totally is okay because you got the f of x. You can calculate n minus 1, but the result is not in 1. So,
yeah. It has to do, I think, it's subtleties. I also have trouble understanding it, but I think it has to do with the definition of the set itself. Let's think about it after. Yeah, I also, when I looked at it last night, it's very subtle, and it's very similar. Need to ask the question really, where are they different, right? That's the.
Is it did you do this last time when you had a
I don't know.
or some invertibility or something like that?
You never said you need to cover the whole code.
No, I didn't. But
Yeah.
but
This is essentially what.
no, but Hadal is no. That's definitely not
Okay.
totality. But the definition of totality and existence is very subtle. Okay, and I'm not sure that I can explain it well now. I need to think about it. Let's take it offline. It's not so important for our discussion. Okay, but this is definitely fine. Okay, this is legal. All right. So pre-image, which is actually important, is the following. So again, if I have f from x to y, the pre-image, which is my f minus 1, is actually defined. It's always defined on a set. Okay, that's important, and it defines a set of all x's, right? Such that f of x is in V. Okay? So notice that this is not the inverse. Okay? It's not the inverse. Right? So if I have, for example, many x's mapped to the same y, right? Then the f minus 1 of that y, right, would be a set of all the x's that actually point to it. That would be the pre-image. Okay? So it always exists.
This is probably something very important when people talk about hashes and everything. Like when they say pre-made, they actually talk about this small set. Because in principle, you could have different f of x is giving the same y, like
Right.
you know,
For these kind of hashes,
yeah.
what are they called?
Which
The hashes.
resistant hash?
Huh?
Collision resistant hash?
The
Yes.
like the normal hash function, not
Every hash.
cryptographic hash.
Yeah.
Right.
So I think it's just hash, no?
Right. Okay.
By the way, I guess it could be kind of confusing, like to f of something. Yeah. So here you're saying that v is not in x, right? So it's like the domain is reversed because of the.
Yeah, it's
Yeah.
always the function, right? It's f of minus one.
Yeah, but now the f of something is a set, and the input is
Yeah,
also a
but
set.
I think
so, yeah,
that if you take like the f of minus one of v,
yeah, then it makes
right,
sense.
then it's meant to equal v, right?
No.
Or no, and actually that doesn't work, right?
No, the image.
When you take,
Yeah.
right,
Yeah.
when you take the image
Yeah,
of,
it's just a confusing notation.
yeah, you're right. You know what? We can just call it pre-image or something like that, or instead. Because actually a lot of times f minus one also, we use it for inverse. Okay, so now let's just, this is pretty simple. Okay, just think about it as I write it. But if we look at u1, u2, both subsets of x, okay, then we can say the following. We can say that f of u1 union with u2, okay, this is in y, right, is actually equal to the union of the two sets, right? Okay. We can also look at I'm just saving time, so we can actually look at the intersection, x the same, okay? And we can actually do everything also with the pre-image. And actually now that it's not f minus one, I have a problem to reuse this.
Yeah, I'll be
Okay.
fine with the minus one.
Okay, so we can use the minus one. With the minus one it also works. Okay. Okay. For both union and intersection. I'm not proving any of this stuff because it's just tedious. We're going to be engineers today.
Can you give an example of this theorem or sentence?
Yeah. I mean, take, I don't know, which one do you want? Choose one of the four.
Whichever you know is easier for you.
Let's just look at it graphically, right? So we've got like x and y. Okay? And say that we have like 4 points, okay, and 4 here. Just define any function. So this maps to this maps to this also maps to this, and this maps to this. And this is just left, right? So if you want to look at, say, I don't know, look at like, okay, like, we call maybe this U1 and this U2. Okay. So you can see that the union, right, is equal to the union here, right? Because these would be, right, if we now, actually it would be better to do it in a different color. But this, right, here would be that, and U2, right, here would be,
No.
yeah, this point over the middle, right, that. But the union, it still works. Okay. Okay. So, let's continue. Just want to say, just something bothers me here now. Yeah, something bothers me, and you should have told me. And Adele will tell me in about probably 2 minutes. One of the things I said is wrong, but let's redo the example, because that was actually a good example to find out the value. And sometimes because things are so simple, you actually just miss trivial things. This is how it was, right? Okay. So let's examine the intersection.
Yeah, that's
Yeah, the intersection.
I'm quite surprised that you didn't pick on that line. It's exactly your type of thing.
Yeah, I wasn't concentrating.
Okay, so actually, if we look at the intersection, right? The intersection here is null, right?
Yes.
But here it's not null. Right? So this is the intersection. And here it's whatever, it's this point is the intersection. Right? So actually, the notes were fine. They're not mine, right? Actually, the correct thing to say is that if U intersection U is actually a subset of the intersection here. Cool. So, who asked for an example?
Or
Learning by,
learning,
what's it called?
learning by doing.
Yeah. Learning with errors.
Learning with errors.
All right. Okay. Okay. Let's keep going. It's a light session, but I think it's suitable because a lot of people now are under the weather.
Especially me.
All right. Yeah. Okay, this is also along the same lines. So, if we take U in X, okay, and then we look at f of x less U, okay, this just basically says that it's like you take U out of X, right? Right, then if I compare this to, let's do it like that and make it more interesting. If I compare it to this, what can I say about like, right, this set and this set, okay? It is basically the range minus the image of U.
So I think that one is a subset of this one.
So this one is smaller.
Yeah.
Right. Why is that?
Because of the uniqueness. I mean, because
Right.
of
Right.
the direction of the uniqueness.
right? But yeah. But if I explain it in like specific terms, it just means that when if I look at removing some of the x's, right, doesn't mean that I remove all the y's that belong to this image, right? But when I do this, right, this necessarily takes every y that's mapped, that's in the image of u, and it removes it, right? So it can still exist here, but it won't exist here. What if it was the other way? If we had, say, v in y, and we look at, I'm just going to go with f minus 1 just quickly, I'm sorry. Look at the pre-image of y less v, okay? And then we look at x less f minus 1 of v. Okay. So same thing, but on the x side, right? So what can I say here?
Right, fine.
So what is this, right? We say, we go to the y side, okay? And we take off a set v, right? And then we map it back, we look at the pre-image of the remaining points in x. Here, we take x, and we take the pre-image of v, and remove it from x.
Right,
Equal.
so it's still like.
Here it's equal.
Ah,
Here it's equal. Just test the specific point, right? If you removed, right, a certain y, okay, a y that was in v, you removed it, right? And then you map it back, right? So it will potentially,
Give all the
it will remove an x,
Yeah.
right? But then here you just remove that x. Right? It's the same.
yeah, you remove the text, but not
Okay.
necessarily.
because there can be like different texts that give the same V, right?
There are.
It's not
yeah,
that.
but you
that's
no,
not-
but you removed.
But no, but on the right side,
You removed both of them.
But on the right side, you remove.
If you have a y that has two x's, two different
Yeah.
x's that lead to that y.
Okay.
Yeah.
So you remove
You remove the y,
Right.
so you remove both of them.
Both
those
x's.
x's.
There.
And
How
here
about the other
you
side?
remove the y as well, so you remove
It
both
will
x's.
because
It's exactly like the problem that we have here basically doesn't exist here. That's all we're saying, and it's also from uniqueness.
Yeah.
Okay?
yeah, these are all good things to know for hacking.
But to find people that have made these mistakes.
Yes.
We'll say that if we have two functions from x to y, and then g from y to z, okay, then we can talk about a composition of, say, right, g of f, okay, or g on f, and the order does matter here, okay, because you obviously can't do f on g because f the domain is x and g the codomain is z, so you can't do that, right? And we can also write these, can write it, right, we can add x here, whatever, but we can, it's also g of f of x, right? F of x is y and gy, so the result is in z. Okay, and that's a function composition. And this actually does create some interesting things. One thing that you can say, I'm not gonna, let's just add like age that goes from Z to W, okay? And then let's look at the composition, right? It would be H, G, F, right? Just check that so actually, composition is associative, all right? So you could do H of G of F, and you could also write it like this. You can actually compose these two first, and only then compose the result on it. Okay, so we've got this associativity property. We can prove it. We're not going to. Okay. All of these proofs are pretty simple. They're just annoying, but they're simple. Okay. An injective function. Okay. So, I think I'm just going to draw it because it's just much easier to understand. An injective function really defines that it actually makes uniqueness both ways. Okay, so
Injective זה חד-חד רכיב.
yeah. It's one. It's also called one cloud. Okay, so this, for example, would be injective. Okay. If like I added this, then it's no longer injective. Okay. Now, if we've got two injective functions and we create a composition of them, okay? So we've got f of x, y, x to y, and g, y to z, and they're both injective, okay? So
זה חד ערכי, לא חד-חד ערכי.
yeah.
It's only
It's only one to one. Yeah, it's not on to. It's only one to one. We'll talk about that.
שזה על, שכולם
Yeah, we'll talk about that.
נכון?
Yeah.
אבל אני לא מכיר אחד הוא חד-חד.
יש חד-חד
יש
ערכי.
חד-חד ערכי.
חשבתי שחד-חד זה עם
Okay. So no, it's not. It's just one to one.
Okay.
That's all. But if I've got two injectives, okay? All right, and notice that they share, like the domain and the codomain I shared. Right? So what can I say about G of F
Will be
in
injective.
terms of injectivity?
It will be.
It will be injective.
You always go.
Okay. Why is that?
It basically means invertible, so you can go back to the first one and then back to the.
Exactly. Okay. Do I need to draw it?
It's better to draw.
Okay. Okay, so let's say that this is right like this, and say that here we'll make it tricky. This is the second function. Okay. So you can see if you use this, right, the composition, right, is actually just this one, right? That's all it is. Going from here to here, the composition of these two functions is just this red arc. It's injective. Okay. So the composition of two injectives is injective.
Why don't you use your own input space? Like the.
Because otherwise it's not interesting. And I don't need to.
And you don't have.
I mean, you know, whatever. Yeah, I've used all my input space.
The first one, I think. the
Actually, no. You know what? You're right. You're right. You're right.
Because
You're
then the
right.
second one
You
is
are
not,
correct. You are correct. That has to be done. You're correct. Yes. Okay.
Yeah,
Right. Otherwise, I don't have. Yeah. But this still is just as interesting. You're right. This would also be in there, right? So it would continue to be injected. Okay. I'll leave the drawing because actually I think we'll use it. But let's now imagine. I think this is the next thing on my notes. I think it is. Yeah. Okay. So let's imagine now that we go the other way, right? We first of all say that the composition is injective. Okay? And then we ask, do they both need to be injective? They're like, or not do they both need? If this is injective, what can I say about F and G, if anything? Okay?
even to say both, if the composition is injective, does it always imply?
Yeah. Let's just, you know, just to, let's just do it so that,
Yeah, it seems
We
that
don't-
they don't have to be injected.
right? This is X, right? This is Y. And this is C, right? And then this would be G, and this would be F. Okay. So do either of these have to be injective if this is injective?
I don't think so.
G doesn't have to be injected because you can.
Yeah, I know that.
I agree. G doesn't have to be injective.
Yeah, because you can put the
But what about F? Let's
F also doesn't have to be injected.
so let's try and
No, we have to.
just a sec. Let's try and create an example where F is not injected, okay?
Because you can't
And
separate.
see what happens. So we can leave these arcs that exist already, okay? I'll just add this. Okay? Now I'm going from X to Z, right? Because now it's not injected, right?
Yeah.
I've got two of these going to there.
No,
Okay.
but
Yeah,
if
but
you
you
didn't
can-
have the arrow from Y to Z, then it would be fine.
Huh?
If you didn't have the arrow from Y to Z, then it would be fine.
Yeah. But
And
then,
then F wouldn't be injected. It would be still injected.
okay. If F is not injective, okay, the only way that this whole thing is going to remain injective is maybe if you cancel this error.
Right.
But
Okay.
then you've got the problem that Ido picked up on before,
Which
that all x's have to be met.
the thought X is a
Yeah, they don't have.
Yeah. So since they all have to be met, you'll
okay.
always get stuck with this. All right. So if this is true, this actually leads to F injective always.
Yeah.
Okay.
Actually, if you,
But not G. G can be anything.
if you restrict the domain like to be exactly the range, so everything should be injective, right? Like the only way you can make G not injective
The
is by making
sizes. Okay.
by making the range like the image of F,
Yeah.
not the full Y. This is the only way.
Fine. But we know we already said that the codomain can be larger
Yeah.
than. Than
Wait,
the
how can G
domain.
be not? How can it be injective if G is not injective? If you
okay.
have everything in Y to the same Z.
Right, so you want the other example. Okay, so let's make this injective again. Okay.
Take the arrow from.
So this let's just net this to here, just for the heck of it. And let's now,
No,
What's the claim? I mean, I'm asking what is the claim that you wrote?
just a sec. The claim is that if the composition is injective, then necessarily it
Oh,
is
it's
injective.
proposition. Okay.
But G can be anything, right? Can be injective or not. So let's just make G not injective, okay? How do we do this?
You need to
Actually,
make
I
it-
don't need this point.
Yeah, you need a point in what?
I need a point here,
Yeah.
right?
Map it with, yeah,
Right.
somewhere,
Like,
Any-
say,
to any point.
to any point,
Yeah.
right?
Now G is not injected. Yeah.
Yeah, my confusion was because I thought it would remain G and F injective, like F is injective by itself, and then it hits to F injective, so it don't means. But yeah, never mind. It was
No, maybe you need to
additional thing.
put like
Just a second.
brackets
Brackets,
around the G and F injective. You wrote like
That?
yeah.
Okay. Alright. Okay, notice that, just so we don't get confused, right? This makes F, this thing that we're looking at, the composition is injective, right? But I can also now add another point here and connect it to here, and then this would be injective, this would not be injective, right? But then that's not a theorem, because that theorem
Yeah.
says that first of all the composition is injective, right? And not the other one. Because we said that the other way we have to have both of them injective. To necessarily lead for the composition to be injective. Okay. Let's now, I'll leave this because I'm writing it. Okay. Surjective. Okay. Surjective, or it's called onto. Alright. Yeah. So, surjective is like the dual in a sense, okay? And a surjective function basically means that we cover, that the range covers the codomain. Everything is mapped. Okay? So, so this, for example, is not surjective, okay? We need to cover everything. Now it's surjective. I don't care how I got here, but I want full coverage in the image space, okay? That's surjective. And then let's again look at what happens, first of all, right, at the compositions, right? So the first thing that we'll say is that maybe the trivial thing. What happens if F and G are surjective? Composition is surjective, right? Okay. Now, why does this happen? Like, what happens if only G is surjective?
It's also subjective. The composition.
No, because
G is
the
the
F,
second
F
one?
might not fill the whole G
Yeah.
domain. Yeah. So
Let's look at that example.
Okay.
Right? In order to, like, if you're surjective here, right, you need, you not necessarily, but maybe you need all the arcs here in order to cover this, right? If you remove some of the arcs here, right, because, or you don't remove, you don't map the whole range, or the whole, you don't map the whole codomain in your first function, right? Then maybe you'll miss an arc here, and now it won't cover the output. So you actually do need them both to be surjective in order for the composition to necessarily be surjective. Now, let's ask the maybe more complicated question. What happens if this is surjective? If the composition is already surjective, okay? Then what can you say again about F and G?
G has to
And
be.
G must be such.
G must be,
Of course, must
but F could not
Right.
be.
Right. Because if G is not surjective, then there's no way to map everything, right?
Mm.
But F, we can find instances of F that still excuse me, that still cover the whole, the whole input space, or not the whole input space, but enough of it such that the output space is all covered. Okay, so right, we had injectivity and surjectivity, and now let's talk about bijective. So bijective is simply when we go and combine the two. We've got injective and surjective together. Okay, that's bijective. Now, right, it's been said before that if we're bijective, actually the domain and codomain have to be of equal size, right? And you can also think about, we haven't said about an inverse, but actually a bijective also creates an inverse, and then once we invert everything, we have to cover the domain down, right? So we can, I'm gonna skip a little bit here. We'll just get straight to the compositions. So obviously, if both functions are bijective, and we compose again G of F, then G of F has to be necessarily bijective, right? That's simple. Now, if we say that the whole thing is bijective, then still, they both need to be bijective.
Because of the previous two proofs.
From
the previous two proofs, like
right,
in one of them one is, the other one this.
Right. Because bijective is injective and surjective.
Yeah.
Right. So from injective, from them both being from one of them has to be injective, the other one has to be surjective. Right. So if we check, we'll see that this immediately implies that they both need to be subjective.
They both need to be subjective?
Bijective.
I think of an example.
Let's see. Let's see what happens. Okay. If they're both bijective, if the composition is bijective,
No, they don't have to be. You can map to the same point in the middle, and then the
so
middle
let's
one.
see. Let's see. So
No, that's what I thought. but-
if the composition,
No, it's not correct, because X can't be mapped to truth twice.
No, this is exactly what I want to show. The full, like the composition will be.
let's see. The composition is bijective, right? That's
It does
that means, right, immediately that this has to be surjective and this has to be injective, right? Necessarily. So we need to have a whole coverage here, right? Let's do it like this. And here we always need, like, right, to start with everything. Right? Let's take, for example, something like this. Okay? This would result in, like, if we can obey it with these sizes, then obviously it's not bijective, right? So we can't invert it. Okay, so if this is injective, right, this means that we've covered at least 5 points in the middle, right? There has to be, there can be more, but at least the size of the input because it's injective, right?
But why take this example?
Hmm?
Did you have 4 and 5 in the middle?
I can have 4 and 5 in the middle, you're right. So that would be like doing 6 here.
Then you map 5 to 5.
Then I map 5 to 5.
And then you map
The input, like x and z must
yeah,
be
and
the
then
same
you map
size.
the 5 to 4. So that's projective, that's injective.
But is this
But
budget?
that,
No, it's not bijective. No,
ah, right, so this is not like, yeah, bijective.
no, but the x and z must be the same size. And
Hmm?
x and z must be the same size, so you can be bijective.
No, one second. No, that's why I said 4 and 5.
Okay.
Maybe let's give some input.
Ah, it's
X
again
and
that,
Z
that
have to
every
be the
x
same
must have
size.
y, okay.
X and Z have to be the same size.
Every x must have
Yeah.
y.
It can't be bijective any other way.
I think that like we can look at it more deeply, but I think that in a sense, it could have only happened if we didn't need uniqueness, because if it needs to be invertible, okay, then the middle shouldn't matter. We should be able to just throw it out.
Right.
If the middle matters, right,
Yes.
and that means like the only way that you could, I mean, this could be like a sketch of proof, but the only way that this could end up being injective is maybe if we did something like this, right? We like opened and then closed, but then this is not a function.
Either that or you get rid of the totality. And then
Yeah.
it also works.
Yeah, I agree. The totality, yeah, but that could, then you could claim that, right, to get rid of totality, then you could also make
Make points
make
in
a
the
bijective on 2 sets of different sizes, right?
You can add points in the middle that don't matter for you.
Right. Oh, I understand. Like you use totality in the middle. Okay. Yeah. Right. Okay. Let's just see. Okay. So let's talk. How are we on time?
11:34.
Okay. We started late.
Bit.
Okay. I actually, we're nearly done with the functions part, and then I want to go back to the isomorphism. It's quick, but I think it's important to finish it today. Okay, so let's just define an inverse. Okay. So we will say. Okay. We will say that we've got f and g, okay? And we will say that g is the inverse of f, the inverse function, okay? If the following composition, g of f, is actually the identity function, okay? Well, we can make it like this, right? And it would be the identity of x, right? Because we start with x and then, sorry, didn't make a slight change. Start with x, end in x, okay? So if this is true, then that's when we call G the inverse of f. Okay, and I think, I'm sorry, but we would probably mark it G equals f minus 1. That's where it gets a bit tricky with this regard. I don't know, they did these notes as well. Okay. And obviously, right, if f of G equals the identity in Y, then this doesn't necessarily, right, the two don't necessarily need to happen. But if they both happen, right, this is called a left inverse. Yeah, this is a left inverse because we always look at the inverse function. G is the inverse function, it's a left inverse, and this is called a right inverse. Okay, and if they both exist, then we say we just call it inverse. Like if G is the inverse of F, then it's both the left and right inverse. That's what it means. So now we can state this lemma again without proof. So we say that if we've got just f, and necessarily we need to say that x and y are both non-empty sets. Otherwise, it doesn't necessarily happen. So, in order for like existence of a left inverse, right, requires, and it's actually if and only if, that this, sorry, it requires that f is injective. Okay? To have a left inverse. Okay? Should we see one? Right, so we're actually, right, if we go from x to y, and then we want to find something that goes back to x such that this is the identity, right?
All points of
Right.
x.
If we have 2 points mapped to the same place, right, then there is no way with the function that we can decide where it came from, right? So f must be injective. Now, if we have a right inverse exists, what does that say about f? That f must be?
How do you call it?
Surjective.
Surjective.
Right? And this is easy because if you don't cover the whole output space, you can never actually go back to the input space, right? Okay. Just think,
Doesn't it need to
you
be?
need to write it.
You need more than that. No, it's not enough.
No.
It's not enough.
We're not saying that. No,
No,
just a
it's
sec.
only
Just a sec. Just a sec. Yes,
It's not
just a sec.
Yeah.
Y, x, and y, right? This is the right inverse.
Yeah.
Okay.
Yeah.
Now,
X to Y.
if you're starting with, you're covering all of y just because
Yeah.
you have to. If this is not surjective, this is one direction, right? If this is not surjective, then there's no way that you can create the identity, right?
But then why?
No.
Huh?
Yeah, because then y to x you don't have totality.
No, it's not just totality. It needs to be the identity. That's the definition of inverse.
Yeah, but it's not even a function.
Huh?
It's not even a function.
Right, like suppose like the inverse is not even a function. No. But if I do cover the whole output, right, that's what we're saying. That's
Maybe if you wanted both sides.
right. If f is surjective, right? So one side is proved, okay?
One side.
If it's not surjective,
Then
then
No.
then the right, like if this doesn't happen, then necessarily there's no right inverse, right? Now the other side is that if it's right inverse, then it has to be surjective.
No, we've
Ah.
flipped it. No, we get it. You said the same thing twice, I think.
Okay.
Yeah. Now you have to.
If
prove
this
that-
doesn't exist, just a second. Okay. If this doesn't exist, this surjectivity, right? Then I can't invert.
Yeah, for sure.
Okay.
Right.
Now let's assume that I can. So I show, right? What did I show? I showed that.
That if there's an inverse, then it's surjective. Oh,
No, I showed that.
Surjection does the inverse.
I didn't show that if it's surjective, it has to have an
no. You show
Right.
that if it's
Right.
an
It's in
inverse,
the-
then it has to be
Right.
surjective.
Now, if it's surjective,
Yeah.
Mhm.
okay, that just means that this is all math,
Points.
but this is also all math,
Right.
right?
Mhm.
Now, I know that if this is all math, right, then
Take an example.
let's take an example.
Yeah.
Let's take something like this, right? Okay.
Mm.
That's not allowed.
Huh?
This-
Why? That's
this won't,
subjective.
this won't work like the other way around.
Just a second.
Okay.
Just a second.
That's not surjective.
This is it.
No, but now look what it implies on here, okay? Because the sizes match, okay?
Mm.
So, I mean, let's imagine that I do this, right?
Yes, it's
But I don't have any definition here yet, right? I don't like, this has to be subjective. This can be anything, that's what we're saying.
So I don't get, but you didn't
It's
draw
not
surjective.
inverse. You
But it's not surjective. What you draw.
No, I'm just saying, I'm just trying to, I can
He
draw
wants
the
the
whole
whole
thing,
thing.
okay?
This
Yeah,
is
Yeah, let's
all-
take everything, yeah.
And just take it,
Yeah. Right.
okay?
Yeah, okay.
This is, right,
That's surjective.
Yeah.
okay. Now,
Now we need to replace your second element.
now, let's for example, do this, okay?
This is not inverse. Right?
This is not inverse, but we're starting with surjectivity. We're not starting with inverse.
Ah,
We're starting with surjectivity and
Okay.
we want to get inversion, right?
Mm.
So now we need to ask, what's wrong with this picture? We just say, I think, yeah.
like your example.
Trying to see what's wrong with my example.
You just didn't build the inverse right. You
Wait,
need to change.
Wait.
You're asking about the existence of the inverse. It's not that every function that you draw will be an inverse. You need to build a specific function. You need, this is the...
You're correct. You're correct.
But you can build it.
So, right, so this, you're right.
Actually, you want to assume the opposite. You want to say, let's say that it isn't surjective, and then you need to show that the doesn't exist.
Right, you can do it like that. But no, but what Ido said is also valid.
Yeah, but it's not a proof.
Huh?
But it's not a proof because it's only one example.
Right.
Yeah,
it's not-
it's just for.
I agree. But like, unless you can show that there is no, unless you can cover the whole space and show that there is not even one case where you can find the function that inverts this, right?
Yeah.
Okay,
You're not going to draw.
let's do it. It's only 4 by 5 points. Okay. Fine. Alright. So actually, if this is surjective, we're claiming that there exists an inverse. Okay. Which is pretty easy to see because there will always be. All you need to do is like take the bijective, right?
Yeah, but if it's not surjective, if it's not surjective,
If it's not
it's
surjective.
clear that there's one y
Which will
that
not
you
happen.
can't reach to.
Yeah.
So there's one y which
So-
is not invertible, and that's it.
Okay.
Yeah.
No problem. I'll let you think about what you said because I think that before we said that that's the other direction of the proof.
Oh, what?
Doesn't it?
No.
This is how we
No,
we
it is-
describe the other direction.
No.
No?
No.
Okay.
And the other.
It's fine. And the main thing is that we're all convinced. Okay.
Yeah.
Let's do this without proof. Okay. We say that that we can get like a two-sided inverse, right and left, only if f is bijective. Okay. And you can do this yourself. It's I think it's very similar. Okay. So I think that this is